The final topic that I would like to discuss in the context of the reactions of enolates and related topics is that of conjugate addition. Okay, so when we talked about the aldol condensation, the product of an aldol condensation is actually an alpha beta unsaturated aldehyde or ketone, depending on what kind of molecule you start with in your aldol reaction. So a little more about these compounds. They actually come back again, and there's a little more chemistry to talk about. Alpha beta unsaturated aldehydes and ketones are electrophilic at both the carbonyl carbon and the beta carbon. Okay, so if we look at this diagram here, we all know that there is a partial positive charge on the carbonyl carbon and a partial negative charge on the carbonyl oxygen. But what's not intuitively obvious just from looking at this is that the beta carbon, which is participating in a carbon-carbon pi bond, also has a partial positive charge on it. And in order to understand this phenomenon, we need to look at resonance structures. Okay, so it's possible to draw a resonance structure with a positive charge at each electrophilic carbon. So you may recall when we started talking about the chemistry of carbonyl groups that we can draw a resonance structure for the CO double bond in which you just have a single bond and a positive charge on the carbon and a negative charge on the oxygen. We said we don't like that resonance structure, but it's still important for explaining the reactivity of these compounds. Well, if it's an alpha beta unsaturated aldehyde in this case, this carbocation resonance structure is actually going to be an allylic carbocation, which means that I can draw another resonance structure in which I move the CC pi bond and therefore put the positive charge on a different carbon, namely the beta carbon. Okay, so it's this extra resonance structure here that explains the electrophilicity of the beta carbon. And as a result, nucleophiles can react at either position. Okay, so in the top case, you have a nucleophile undergoing what I'm going to call a simple carbonyl addition reaction, where it just ignores the fact that there's another CC pi bond there, does exactly what you would expect it to do, adds to the carbonyl carbon. The final product is an alcohol. And in this case, because there is a double bond next door, the product would be an allylic alcohol. However, the other mode of addition is where a nucleophile reacts with the beta carbon and forms a bond to the beta carbon. We're going to look at the mechanism of this in detail in the next slide. But in the end, we end up maintaining the ketone, forming a bond between the nucleophile and the beta carbon, and then forming a CH bond from the alpha carbon to a hydrogen. Okay, and this reaction is called conjugate addition and is sometimes called 1,4 addition. Where the term 1,4 addition comes from is the initial product that you get after conjugate addition is an enol. And the nucleophile and the hydrogen that gets put on are spaced 4 atoms apart instead of being spaced 2 atoms apart. And those are clearly indicated in pink on this diagram. Okay, so the mechanism of the 1,4 addition, we're going to have the nucleophile attacking the beta carbon. The carbon-carbon pi bond moves over to form an alpha, a C alpha to the carbonyl carbon pi bond. And then, of course, we then break the CO pi bond and put the electrons onto the oxygen. This now leaves us with an enolate, and then in the second step, this enolate is going to protonate. Instead of actually forming the enol, I have this protonating directly on the alpha carbon, which is what it's going to want to do, to give us the aldehyde that now has a nucleophile having added to its beta carbon. Okay, so we know that nucleophiles can add to either position. We now have to address the question, when do we get 1,2 addition and when do we get 1,4 addition? Well, let's look at the experimental data first and then try to understand it. So the facts are that strongly basic nucleophiles, which can add irreversibly and rapidly, will undergo 1,2 addition, whereas nucleophiles which add more slowly and reversibly will undergo 1,4 addition. Okay, so a couple of examples of this. What's something that adds rapidly and irreversibly to carbonyl groups? Well, lithium aluminum hydride is a good example. So if you take an alpha beta unsaturated aldehyde and add lithium aluminum hydride and ether, followed by the aqueous workup that's necessary for a lithium aluminum hydride reaction, you're going to get neat reduction of the carbonyl group to give the allylic alcohol as the product. On the other hand, if we use methylamine as the nucleophile, this is now a much, much weaker base. pK of its conjugate acid is about 10 instead of the pK of its conjugate acid being 35 in the case of hydride. This is now going to undergo 1,4 addition, so we maintain the aldehyde functional group and the methyl amino fragment ends up bound to the beta carbon. Why? Well, this is another case of kinetic versus thermodynamic control. So the 1,2 addition product forms faster, but the 1,4 addition product, the conjugate addition product, is more thermodynamically stable. So the kinetic argument is a fairly simple one, and you can figure this out just by looking at the curved arrows in the mechanism. So the 1,2 addition mechanism involves less reorganization of electrons. You're just doing all of your work, all your chemistry at the carbonyl group. You ignore that extra carbon-carbon pi bond. So with less reorganization of electrons, the reaction happens faster. And the curved arrow analogy is that a simple nucleophilic addition to a carbonyl group only requires 2 curved arrows. One to form the bond between the nucleophile and the carbon, and the other to break the carbon-oxygen pi bond. Whereas, as we saw in the previous slide, the 1,4 addition mechanism requires 3 curved arrows. Okay, what about thermodynamics? Well, in a 1,4 addition reaction, the CO pi bond, the carbonyl group, is maintained, that's shown in green, and you form a new carbon-hydrogen bond shown in red. Whereas in a 1,2 addition, we maintain the carbon-carbon pi bond shown in green, and ultimately we form a new OH bond, which is shown in red. Well, recall from our discussion of enol versus keto tautomers that the combination of a CH single bond and a CO pi bond is stronger than the combination of a CC pi bond and an OH sigma bond. That's the reason why the keto tautomer is favored over the enol tautomer. Okay, so that now, since 1,2 addition is reversible with less basic nucleophiles, the 1,2 addition product will form rapidly, but then it is capable of reverting back to starting materials. And what you need to think about in this case is imine formation, right? Because the nucleophile that I used for the 1,4 addition on the last slide was a primary amine, which if it was going to react with an aldehyde or ketone, would probably go on and give you an imine. You can start down that pathway. You can add the amine to the carbonyl carbon. But remember that imine formation is a reversible process, and that reaction can go back to starting materials. However, while the 1,4 addition product occurs more slowly. Once it occurs, it will not go backwards. So this product, the 1,4 addition product, will eventually, if you let everything come to equilibrium and give it enough time, this product will build up. You've seen this phenomenon before, and the place that you saw it is in the context of forming a kinetic versus a thermodynamic enolate through deprotonation of a ketone. Okay, so remember that the kinetic enolate is the less when you remove one of the less substituted, more sterically accessible hydrogens from a ketone. The thermodynamic enolate is when you remove one of the less sterically accessible hydrogens. That leads to a more thermodynamically stable product. And which product you got in that case depends on the base that you use for deprotonation. Okay, so in this case, whether you get 1,2 addition or 1,4 addition depends on how strong of a nucleophile you have, whether it wants to give you the kinetic 1,2 addition product or the thermodynamic 1,4 addition product.